Today we're going to do curl and divergence. Divergence, just like in the movie Divergence. I actually was thinking, did they actually mean that? Yeah, they actually mean that. I will explain you. From English point of view, it's so interesting. It took me some time to realize that's the same thing. So we're gonna learn, we already learned qualities of the field being towards your face, against, helping you when you bike. We learned that. We learn how fast the field can be. So derivatives showing you that, and so on. Conservative fields. Now it's a cool thing to figure out if a field curls, that means spins, rotates. And if it spins, how strong the spinning is. So that will be a number or a vector showing us the spinning properties of the field. And divergence of the field. I thought divergence just a fancy word, and it's div. Everyone know it is div. Now they actually mean dispersance. How fast the field just disappears or disperses. Anyway, it's super cool from physics point of view. So if you like physics, even if you're not a physics major, this is pretty awesome. So by the definition, F consists of P and Q, and then we're adding third dimension R. F, that's a field, right? Then divergent, div of F, is the sum. Remember we had before derivatives, right? So that was derivative with respect to x, derivative with respect to y, derivative with respect to z of each component, p, q, r. What if we're going to add those together? That gives us divergence. So it's versus, comparing. That is a pretty cool idea. Let's add all the partial derivatives together and see what is going to show us. Apparently, this number, which is a number, will show us how fast, if any, if at all, for example, a liquid. In this chapter, it's easy to imagine liquids. Before, I like to imagine black holes and gravitational forces. Here, liquids are easier. How fast or how much a fluid will disperse. When you drop a water on the car, it falls off pretty fast. But if you drop honey on the car, because of the viscosity of the honey, dispersion is not happening fast. It actually accumulates like a little towel and then melts. That is pretty cool, and this quality can be explained through divergence. Example. If I give you, so given F, and F is, P is just X, let's do X squared, Q is Y squared, and R is Z. Three-dimensional field. Find divergence, div of F. So that will not be a list of derivatives anymore, like we had for gradient. That will be the sum of derivatives. That's a pretty cool new thing to remember. In general, the last 3 lectures will have lots of new formulas, unfortunately. So that's the bad part. It's the class. This class accumulates material so much, it grows in such a higher level, preparing you for upper level of STEM knowledge, that it introduces lots of new formulas. So you will have to figure out how to remember that. 2x plus 2y plus 1. So we're adding instead of listing it. So that is the example how to create. Yes.
Sorry, will there be more content from later parts of the class on the final, or is it all just ready?
Oh, good question. The final exam, I'll post an announcement about this. Usually lots of new stuff, and then like one problem for each, some kind of old stuff. Yeah, I will be preparing you for final, so don't worry about it for now.
Thank you.
This week you have other exams, right? So that's your priority, finish other exams. Finish homework as soon as possible. Finish all the small deadlines. That project, that paper, that blah blah class. Make this presentation as soon as possible. Then you have lots of time for the important classes, which not necessarily mine. Like any important hard stuff, make sure you have more time for that. So finish the easy stuff or time-consuming stuff fast. Computer science. So find just in general F, and then if I want a number, so find div of F at, and then I will do 1, 1, 1 at the point 1, 1, 1. then it will be, guess what? You plug in. It will be 2 plus 2 plus 1, which is 5. So it's not a vector, it's a constant. So if we got 5, what does that even mean? That means that f expands at the rate of 5 at that location, because it might be different locations and stuff like that. So let's check this out. Interpretation is expansion. Write down several words. Expansion. So it's called divergence, right? Divergence. I'm trying to figure out other synonyms in the English language, especially for the people who don't speak English as the first language, foreigners, Hispanic students. We have many people who are actually really cool learning STEM, not in your own language. Imagine learning this class in Japanese. People who know Japanese, oh, piece of cake. No, this is hard. So trust me, I had to figure out all of this as well fast while doing research. Divergence, expanding, spreading, right? Spreading. And I have some other synonyms at the bottom. So here's how it looks like. 5. F expands how fast? At the rate 5. So water expands fast. When you drop, the water drops, just goes away. That means also particles get farther and farther from each other. That's the definition of expanding, right? Dispersing. While honey, you pour honey and it's still all kind of together. Particles are still close to each other. So dispersion rate will be slow. Some things don't disperse at all. They just stay. Like mercury, kind of don't disperse. You drop the mercury, it's still there in a little tiny, very beautiful ball, which is very dangerous. So that will be dispersion 0, I guess. So that will give you this number 0, and you know what it means. Yes?
Will div f be written any other way?
I don't think so, no. Usually df, yeah, D-I-V-F. You mean D-I-V?
Yeah.
No, this is international notation.
Oh.
Yeah, thank you for asking. That's pretty clever. So what it means to have 0 divergence, just like told you, mercury, if you don't recognize this word, it's like this metal drop. You drop it, it doesn't go anywhere. So then we have this kind of word, I like it, incompressible. Incompressible. High respect to people who don't speak English as a first language, who went to physics class, to physics major. Like, those words are long. Incompressible. Compressing, shrinking, and then they not compressible and not expanding. I like non-expanding because I know what expanding is. That is when this number is 0. So I still have actually a thermometer. When I get sick, I have a thermometer which has mercury in it. It's like very old school. I brought it from Ukraine, and then when I brought it, I find out it was illegal to do that. I don't know. Who knows? You're not supposed to own mercury thermometers anymore for obvious reasons. But in my culture, it was so popular. Like, I did not even think twice about it. So I still have it. It works for 10 years already, and it's all very old, probably 30 years old. I'm pretty sure. And I did not know it was illegal to bring it. It's like, oops, too late. Now, let's, right after this, jump into the curl. So I will give you these formulas in a second. But let's figure out this idea. What does it mean to have this in 3 dimensions? I mentioned to you before that we're going to go into upper dimensions in other classes. But curl actually briefly covers it before Stokes' theorem. It's one of the applications of Stokes' theorem. And we're going to do that a little bit. So if f is conservative, but it has this third variable now, you find this small f somehow. So it should be possible to find. And you find all those partial derivatives, and they're the same because how good f is. Then you find out that all those differences give you zeros, not just one difference, which we just had in the exam 3, but all of those differences give you 0. Q and P, R and Q, R, P and R. You don't have to write down yet. So there is one amazing operation, called curl, that takes care of all of this at once. Curl of f. Let's write down the formula. curl of f. Curl, C-U-R-L of f. Let's call an operator. That will be a vector, not a number like before. So 5 was number before. That's how fast something is dispersing, diverging. Now it will be curl. Curl has this notation, cross product between partial derivatives and f. That is a notation. It's not actual. The left-hand side of this product is not even a function or a vector. It's just a sign of the derivative. So that's called a notation, but it's fine. It is cross product, cross product. So the answer is a vector. We know that. Cross product in my culture called vector product. So the answer is a vector. And the easy way to remember it is just like before we have I, J, K. Then we have partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. And then we have those P, Q, R. P, Q, R. So, again, the second line does not make sense. The second line says take derivative with respect to x of, and there's nothing there. So that's a notation. The second line says of, and then you have to multiply carefully by some P, Q, or R, and it'll be of P or of Q. Which is, let's continue the formula. The answer will be a vector this time. And now we remember, hopefully, it's a plus minus plus. I, that will be the I component over here, takes care of these two, the right bottom square. Cross product gives me partial derivative with respect to y times r. So r goes here. Minus partial derivative with respect to z times q. And it's not times, it's of q. Blah, blah, blah. That's a little bit too long to write. So people actually have this nice short notation. Short notation is r with respect to y minus q with respect to z, comma, p with respect to z minus r with respect to x, comma, q with respect to x minus p with respect to y. That is the formula. You can get frustrated that this is hard to memorize. That's why I actually don't. I don't remember the box. I remember the previous notation. And then I just know how to do matrices. So I know how to find determinant of the matrix. So I recommend not to memorize it unless you have good memory, then do that. But it seems like it's from y to z, from z to x, from x to y. So it seems like the order is y, z, x, and it goes back to y, like so. But I don't remember this box. I remember the determinant. Like so. So curl explains properties of curling, swirling, creating whirlpools. How cool is that? So let's practice finding curl, and then I'll show you some really awesome applications. Example, your homework basically will ask calculate those things, and this is perfect for the exam. Multiple choice, very perfect. Yes?
So when you find the determinant, you don't need to do like I and then negative, then positive K?
Oh, we did. A very good question, where the I, J, K, and where the negative went to. So I is here, minus J is here, and K is at the end. So original one was minus parentheses Rx minus PZ, and then we're flipping it because of the negative sign. So the second one is the only one that is affected by the sign. It's like so. And then we're flipping the order. And also your question is where the IJK left. Either you don't write down the form of the vector. You have this times I minus j times, so either you write it down as the sum and differences, or I like to writing it down in the form of the vector. Just looks prettier. Did this answer your question? Yeah, it's a good question. Questions? Good job, people. Find curl of f where. So this is very nice multiple choice question for the final exam. Where f, find curl, find divergence. Two different multiple choice questions. 0, minus z, and y. And I like to put something simple so you don't spend too much time calculating it. So solution, I mean for the exam. Homework is always harder than the exam. I think you have noticed that. But again, I just dropped your lowest homework. So you don't have to be perfectionist. That's why I did it. You can even ditch some of the homeworks. If you have 100% on everything, technically speaking, you can ditch the last homework. It will give you 100%. But for practice. Okay, step 1. Now the formula step 2 actually calculated, right? Curl of f. The formula is I, j, k. Then I know derivative with respect to x. Derivative with respect to x, derivative with respect to y, derivative with respect to z, and then I put my actually given functions. P is 0, p is a function 0, or p equals to 0. Minus z, q, and r, y. Like so. And now you start actually calculating it. So again, it should be a vector, remember that, not a number. Curl is a vector. Derivative, okay, let me figure out like this. So we have cross product. Derivative of y with respect to y. Should I write down? Or I guess let's write down. Derivative of y with respect to y minus plus. Because, okay, it's fine. Let's do minus derivative of minus z with respect to z. How cool is that? Minus, 1 and 1. Minus 1, comma. Then I will do these guys. Derivative of y with respect to x minus 0, whatever. Doesn't matter what derivative is. 0 is 0. Saves time. Comma, and the last one is the first squared. Oh, and also there was a negative sign for the second one, remember? There's a huge negative sign in front, like so. And the last one is derivative of minus z, but this time with respect to x, minus 0. Did anyone actually calculate why it took me forever to write it down? Derivative of y with respect to y is 1 plus or minus 1 plus, because derivative of minus z is minus 1 minus minus. Now minus y with respect to x is 0, and the other one is 0. Seems like the vector we have is 2 0 0. 2 0 0. So again, note, divergence is a number. How fast something is dispersing, diverges. Particles moves away from each other. The speed is 5 or whatever. Well, curl of f is a vector because of the cross product. Cross product of what? Derivatives times f. Derivative, the times is the wrong one. Cross product times f. Cross product. Good job. I heard you saying what, and then that means there was a mistake. So now I'll show you. It's really cool. I was checking yesterday my notes, and I decided to add some explanation, so I did. What is a curl and divergence from physics point of view? So many people here do physics, or at least like physics. Roughly speaking, divergence measures the tendency of the fluid to collect or disperse at the point. That's divergence. Collect or disperse. While a curl measures the tendency of the fluid to swirl around the point. Isn't it awesome? Divergence is a scalar, a single number, and the curl is a vector. So you don't have to write this down, but it's in my notes. So if you talk about fluid, you can talk about anything else, but fluid here is more Magnetic fields will be also pretty good because you can see if something is stretching you away, that's divergence. How strong the magnetic field's taking you apart. And then swirling, that's curl. But with fluid, I think you imagine whirlpools, and it's pretty cool. So divergence checks if the fluid collects or disperse at the given point. Curl measures tendency to swirl. Examples. The curl indicates how much the fluid rotates or spins around the point. So we got this vector, right? Now I can choose any point and it will show you the tendency of swirling at that location. When you scrub your dinner plate with a sponge, the soap and water begin to swirl around the plate to make it clean, which is the curl, and the water dispersing out of the faucet and subsequently leaving through the drain is divergence. That's pretty cool. I found this like very visual explanation because we all do dishes, right? You guys do dishes. I hope you do. Okay, intuitively curl measures rotations. So curling took me some time to figure out. It's an English word. It's curling. And divergence is also English word. It means divergence. Somehow it did not click. Like for me, math and terminology is one thing and in English is another thing. No, it's literally the same thing here. Okay, so, and before, you don't have to write this down, but before actually, last time, right before the exam, I showed you those little microscopic and macroscopic rotations. So I told you that these guys, the differences, they actually measure rotations. And they can be several, and then the whole integral, line integral over the field that collects them all and maybe show you some big rotation. So it may be this way, right? So curl collects them all, and then it has a very cool property. If curl collects all kind of rotations in upper dimension, then it measures how F rotates in each plane. Okay, so let me try to explain to you. Example. Let me do this. Let's write down this. Curl of F measures how F rotates in each plane. So write this down. That is how it's created from the construction. If each difference is micro rotations, they're happening in some planes, XY plane, ZX plane, and so on. It collects them all and gives you information, not only if this fluid has tendency to rotations, but also where. It's in 3D. Like imagine this stuff like a tornado, it's in 3D. So not only where it rotates, but which direction from each plane point of view. Example, if F is 0 minus Z and Y, curl is 2, 0, 0. Bless you. Don't copy the picture. I will show you how to copy. It's a little bit complicated. So curl is 2, 0, 0. So you first plot the point. It's a vector, right? So we know how to plot 2, 0, 0. So it's a 2 on the x-axis and then 0, 0. And then you connect. Here it is. So that means they decide to move it to be more visual, like so. So that means these places over here, this vector creates a rotation. Curl F is the axis of rotation for the whole F. Now check this out. So draw the system X, Y, Z. Here it is. Put the curl. Here it is, 2, 0, 0. Those blue lines creating axis of rotation. F is rotating around those blue lines. So blue line here, let me make it thicker. Axis of rotation. That means that rotation happens in this plane, like so. So there is a rotation around X, if you see X to be as axis of rotation, so a hand, and it's moving the air or the fluid. But there is no rotation in this plane or on the floor. It's rotating only towards the axis of rotation. Yes?
So you know the direction of x is going to be towards x and not
Yeah.
not towards x.
Well, like a typical vector. So vector points at stuff. Yeah, so vector 2, 0, 0 is 2, 0, 0, and it points there.
Oh no, I'm talking about like the red F.
Oh, you mean the counterclockwise or clockwise rotation? Good question. We're going to talk about this a bit later. Yes, but we do know. Yeah, very smart. So not only tells us if, just a sec. Not only tells us if something is rotates, but it also tells us where. So no rotation. Point here is peaceful. There's no rotation in this point, in this point, in this point. There's no rotation over here, over here, over here. But there are rotations over here, and over here, and over here, and they tend to rotate like so. And also we're gonna learn if you're moving away from the axis of rotation, is rotation just 0 or it slows down? We're gonna learn that too. Yes?
Yeah, like isn't it rotating though like towards us? Like how is it like rotation up above?
Let's see. It's rotating not towards us. Towards you is the axis of rotation, and it rotates around it, right? I imagine it like this. Like this. But the point was that on the floor, there's no rotation happening on the floor. It only happens towards us in 3D, I would say this way. And it only happening because x-axis here is the only one that has non-zero component too. So they say basically in these planes, there's no rotation, it's peaceful. But in this plane, there is a rotation, and it gives us the strength of it and location, and the axis of rotation is 2, 0, 0. Kind of. I'll show you more animation, and I think it will be more clear. But I do know, usually it's not clear at all at the very beginning. So you can write down, curl F is the axis of rotation of F. The most important about the curl, it gives us a very elegant way of checking whether a vector field is conservative or not. We already had the way to check to get the 0 thing, so we're gonna do that as well in 3 dimensions. So F is conservative if curl is 0, 0, 0. This uses Stokes' theorem, which we cover in 13.8, but we never go to 13.8 in this class. So you guys cover it in next classes when you take them. But that's actually like the whole point of this class is to give you Stokes' theorem, and then we don't. So people who teach at this university, they're surprised about this. That Stokes' theorem should be like this, the most important thing. It's kind of as important as, I don't know, Pythagorean theorem. Like you need Stokes' theorem in STEM to work with upper dimensions, and then we never go there. We're like 1 chapter before Stokes' theorem. It's so upsetting. So my colleague just relocated to Brown University, and he's like, finally we're teaching Stokes' theorem. I'm like, I know, we're like 1 step before it. So write down, F is conservative when curl gives you 0, 0, 0. But what are those zeros, zeros, zeros? Those are differences which we already know from the determinant. Each difference gives you 0. I guess you can write down x to y, y from z, z to x, q, p, r, q, r, p. I know it's hard to memorize for me, so I just remember the determinant. And I have like nice introduction here. Conservative vector fields. That's a very popular tool. You find the differences and check if they give you those zeros. In general, think about that. Those differences were important before curl was created. Then people noticed those differences give you lots of information, and they created operator, called it curl, and put everything in that operator. Curl of F. So again, in the previous example, when we had 2, you should understand that this 2 came out of the difference of derivatives. Again, derivatives gives you some kind of rate of change in some kind of direction with respect to x towards there, y toward there, z toward there, blah, blah, blah. So those differences creating some kind of correlations between changes in different directions. And that's why it stretches or curls. So that's why it's 3D behaviors. So we know that, it's fine. And you can write down important fact. F is conservative if and only if the double-side error means it goes both ways. If F is conservative, curl gives you 0, 0, 0. And the other way around, bless you. If curl is 0, 0, 0, F is conservative. So it's if and only if. That means if your calculations gave you 0, 0, 0, now you can notice, oh, the field we just recorded in the space somewhere far is conservative. And the other way around. If you want to check field is conservative, you calculate the curl. And they mention Stokes' theorem here, which goes in the next section. This is a good test for conservative fields in 3 dimensions, 3D analog of what we had before. So let's check. That's a good exam question. Oh, I didn't leave space here. I was wondering. Here is the question. Let me make some space. Find or check if F is conservative. That's a very nice multiple choice question. And then with the B part of it, it has a nice free response question. If F is y squared z cubed, comma, 2xyz cubed, comma, 3xy squared z squared. This field, so question A, is this field conservative? You just need to start calculating this determinant. Cross products again, because it's cross product, we remember how to do it using determinants. So, see, like I confuse people on the exam with a very Russian-Ukrainian notation. I put this line, which basically means is, right? I put a line. Several people ask me if this is a minus. I'm like, oh, Americans don't put lines. I forgot about that. You guys somehow, you do, if it's not a question, it says is conservative, okay? Instead of is, we put a line, because it's faster. And then people ask about this, and like, I forgot about not to put lines. You guys are not very good with commas and semicolons. In our culture, it's a very serious, I mean, yeah, okay, you are. But you have to admit that, do you know many people who are good at it? I don't know, I don't think so. Some people learn it once, and they know how to use semicolons and everything else. But most people, I think in English, they're not requiring it that much. So when I use it, it feels like, yeah. Sorry, hope it didn't sound bad. I feel like I don't see lots of people who do use them a lot. Curl. F. You create a formula I, J, K. And then you have derivatives with respect to x. You don't have to do this formula if you remember the differences, then you're fine. And now you put what they gave you. Y squared z cubed 2xyz cubed doesn't fit. 3xy squared z squared. Like so. And you perform this whole idea with finding determinant, just like we did with cross product. But this time, when you perform all of this, you have to find derivatives fast with respect to each variable. Remember when you struggled finding partial derivatives? Now that's easy. Now I hope so. I hope it is. But now it feels like not that bad. So the first one is I times. I like to put in the vector form, but I guess let's do at least once. I times, just to show you that's the same thing. Derivative of 3x, here it is, derivative of 3xy squared z squared with respect to y is 3x 2y z squared. Got it. Minus derivative of 2xyz cubed with respect to z, 2xy 3z squared. So I did the first one, and now people will have to help me with the second one. That's I component. You can do with a comma if you want. ijk minus, don't forget that. Are you catching up, right? So that's, I feel like that's not very new material. We just have to be careful with minus and plus. So minus derivative of this with respect to x, what does it give you? 3y squared z squared. Agree? So just drop the x. Now derivative of y squared z cubed with respect to z gives you, oh nice, y squared 3z squared. Don't forget minus between, but also minus in front of it, plus k derivative of 2xyz cubed with respect to x. 2, and then what do we drop? X. Exactly. Minus y squared z cubed with respect to y. 2yz cubed. Amazing. Do you understand what we're doing? People like sleepy. Not very interesting. So what is the goal? Do you know? The goal is to check if it's 0, 0, 0. Yes, it is. 3x, so it's 6xyz squared and 6xyz squared, 0. 3yz blah blah blah, 0. 2yz cubed and 2yz cubed, 0. It is indeed 0, 0, 0. Thus, the field is conservative. Answer, it is conservative. If it is conservative, now you can find a potential function if we ask you to, and guess what we do ask you to do that. So answer. Let me move this. So you can write down, the field is conservative. Let me move this down. I found this really cool explanation. Answer. F is conservative. So the big question was to find the potential function, which is exactly the same way we did it before. So to be honest, I have homework solution for you at the end of this file, but that's actually initial value problem. So it has more idea there. But potential function is exactly the same, nothing new. So check out, very interesting what I found today. I wanted to show more stuff. So here it is. What does it mean to have zero divergence, for example? So what happens, what is the concept of zero divergence? It's very important in fluid dynamics and electrodynamics. It indicates that even though a fluid flows freely, the density stays constant. Density is how close or far particles are from each other, right? It's particularly handy when modeling incompressible fluids, incompressible, such as water. In fact, the very idea that a fluid is incompressible can be tightly communicated with the following equation. Let me make it bigger. Let me see. The following equation, which is, that's what I'm trying to show you, this. The gradient times V. This vector, if this product gives you 0, this field's called divergence free. Pretty cool idea, divergence free. That means they don't diverge. That means that the distance between particles stays 0. So that's about divergence. We're talking about, again, about divergence, div. So here's the idea. Divergence-free example is, even if something is swirling, so we're not talking about curl anymore. We're talking about distance between particles. Even if something is swirling, you see, the distance between points stays the same. So that is an example of incompressible fluids or behaviors, when you don't shrink and also don't stretch, divergence-free. While if this piece is negative, then guess what? Something is shrinking. Then particles diverge to a point. So the distance between particles is decreasing. That means something is more dense. More dense. Then if this product is positive, then it's less dense. Stretching diverges, right? And 1 more 0 example stays the same. The distance between particles stays the same. So that is also one of the explanations of what divergence is. So that is div of f, like so, which is sum of partial derivatives, which again makes sense. If you add partial derivatives with respect to x, with respect to y, and with respect to z, and that whole number gives you 0. Partial derivatives tells you changes with respect to different variable, different plane with respect to x, here, y, z. If you add up those together and the number end up to be 0, that means particles do not move away from each other and don't shrink. That makes sense. If the number is positive and big, then everything goes away and it's fast. So it stretches away, say magnetic fields or stuff. If it's small and big, big negative numbers, right? So minus 100. That means something is sinking into one point fast. So that's kind of what I'm trying to explain. Pretty cool physical properties. I find pretty interesting. So expanding with some kind of rate or shrinking with some kind of rate. And also they are talking about the property of being compressible and non-compressible. I also like the density idea, that the density is changing or stays the same. How cool is that? Finally, what is the relationship between we first learned derivative, gradient of f, just collection of all derivatives. Then we learn divergence, the sum of derivatives. Then we learn curl, differences of different derivatives, right? So write down, the correlation is curl of the gradient gives you a 0, 0, 0 vector. Divergence of the curl gives you a 0 number. When something is curling, so spinning, right? Something is curling. The particles are not necessarily shrinking, compressing, or stretching. This is the example here. So how to indicate that quality, that the distance between particles stays the same? Well, that means the divergent is 0. That's the idea here. Don't jump. Thank you. So write down those two properties and I'll show you something awesome. Did you write down? Come on. Don't be stupid. And good. Slowly increasing. Good. Curl of the gradient 0, 0, 0. Divergence of the curl is 0. And this is actually, I don't like the grad curl divergence idea here, so I don't plan to talk about that. What do you think about this? Do you think it's cool? I feel like it's pretty cool. Like, I know students at the very last week are very tired, so it's very hard to be impressed because you have deadlines, you know. It's hard to be impressed when you need to do taxes. Like, it's some chores, right? There's a chores, and it's hard to be happy when you have chores to do. But it is pretty cool. I feel like regardless of that, it's a pretty cool idea. Yes.
So, what is I don't understand the first relation. Like,
oh, curl.
Because I thought when you find the curl, you're doing kind of that, but not really.
So you do it second time. You're right. So we already have derivatives, right? And now you do this whole determinant. Derivative, derivative, derivative. And derivatives are here. That's, yeah, exactly. Very cool. I would say, like, if you imagine slope is a second derivative. Curl is how things are moving around in curling. So that makes sense then. That's pretty cool. A very good question. Let me show you some awesome stuff I found. So Khan Academy is a very nice source of collection of information, and I specifically liked this one. Of course, check it out. They're talking about density and fluids. So here's the vector fields. They talk about derivatives first. And then they say that the fluid, during the fluid flow, some regions tend to become less dense with dots as particles flow away, such as upper middle section. Upper middle, okay. On the other hand, in other regions, particles tend to flow towards each other and dots become dense. Do you recognize this amazing channel? I hope you did. So here are my derivatives, vector fields. So some particles get closer to each other, some particles spread. How to identify that using math, and vice versa. If math gave you stuff, how to know that that is the explanation of that math. Key question for a given vector value function v, how can we measure the change of density? So we learned before in calculus 1 derivatives and integrals. Okay, we know how fast things move, even second derivative, third derivative, acceleration, jump, and that stuff, kind of stuff. Now we want to know how fast they move and get into the group. Isn't it cool that there's a mathematical property for that called divergence? So we can answer this question using a derivative called divergence. It's a variation of a derivative. If we talk more about fluid flow, then it's easier to visualize it. So here's divergence, blah, 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 divergence of V, positive, negative, 0. Positive spreads, negative shrinks, 0 does not change. Here it is. I already showed you that. This is divergence. So negative, more dense. Look at that. That's negative divergence. It gets more dense. So the particles have no choice but to fall into the sink. So visually, I know we all know what sink is. Positive, spreading. The divergence is positive. Going apart. So divergent, right? Diverges. That is pretty cool. And 0. Look at this. And then tell me if you recognize this graph. 0 divergence. Particles don't really spread and they don't compress. This is incompressible field. See, the distance between particles don't change. Do you recognize the shape of those graphs? Those are sines and cosines. Those are waves. That's why trigonometry is so important and extremely annoying. It's everywhere. Like all those waves, they're definitely in the wind and magnetic fields, black holes, everywhere. Electromagnetic fields, everything. That has divergence 0. What does it mean? Why it's happening? So all of this is pretty interesting. That was like very not enthusiastic sign. Okay. Sink example. When something is sinking, see, it's keep going into vector field sink example. That is pretty cool too. So likewise, instead of thinking of a point with a positive divergence as becoming less dense during a momentary motion, these points might be thought of as sources constantly generating more fluid particles. So you will see terminology in physics called a source. Actually, in math homework, you will see it too. That is a source. It gives you more energy, for example. And in higher dimensions, of course, we have that too. Interpretation and all of that kind of stuff. So I put this link. That is pretty interesting. And have you ever thought about vorticity? How cool is that? I really like this word. Okay. I was wondering why I never heard about it from my math major. Because it's physics. Vorticity. How do you say it? Vorticity, right? Yeah, it's like vortex, right? So in continuum mechanics, I mean, that's a cross product over there. Like, why I never heard about that before? Because it's physics. Vorticity is pseudo vector. Pseudo vector means kind of fake vector or almost vector field that describes the local spinning motion of a continuum near some point. Local spinning motion, the tendency of something to rotate. Blah blah blah, along the flow. And it is, guess what? Mathematically, vorticity is a curl but of the flow velocity. That makes sense. So just the curl tells you where things rotate. But vorticity talks about also flow velocity, so speeds. And they check vertex rings and stuff like that. It's a complex flow phenomenon, such as formation and motion of vertex rings. Water, underwater, and tornadoes, and in space. So I found, okay, come on, look at this. Rigid body like vertex, parallel flow with shear, and irrotational vertex. That is so cool. So Wikipedia has lots of cool animations as well. And then the quality of that will be described by the math, which comes from the cross product curl. And you can have different types of them. So relative velocities around the highlighted points, with zero velocity, not zero velocity, and so on. It's pretty cool. So I found, see, how would you describe a rotation of a particle? This is a very nice rigid description here visually. A square rotates. So rotation, and now imagine all of those are molecules or particles, electromagnetic particles. That's so cool. And this is exactly what we're doing right now. You see the differences? This is what we're doing. It's a cross product in Cartesian coordinates. It's a curl. The vorticity is also related to the flow's circulation. So imagine blood circulation. All of this is also using the same math. Stokes' theorem is used here, of course, which we don't learn in this class, but okay. And so on. Finally, I found this cool animation. Go. Look at that. See those squares, how they rotate, or rectangles? That's pretty cool. That not only rotational properties, but stretching or shrinking. That is divergence. Do they diverge or they don't? So now you know the movie Divergence. They meant this. They meant math. You just missed the point, okay? Okay, very nice. Let me introduce the beginning of the next chapter, and then we move on. This homework is due Monday. But let me start the next chapter for 10 minutes, and then I think it's good enough. The beginning also is always very pleasant anyways.